Okay, so today we will discuss the area between two curves again, but we'll see when it is more convenient to integrate with respect to y than with respect to x. So we'll begin with this do now problem. Find the area of the region bounded by these three curves. Y equals the square root of x, y equals the opposite of x plus 6, and y equals 1. So pause the video and let's sketch the region. So y equals the square root of x is the red curve, and it's again part of the equation y squared equals x, but we take the positive square root. Y equals 1 is the horizontal line, and y equals the opposite of x plus 6. Well, again, a negative slope, and when x is 6, y is 0, so I sketched the x-intercept here. All right, so the region bounded by these three is this piece. It looks kind of like a triangle, but one side is curved. So the next thing we must do is find the intersection points. We have to find the intersection points for our limits of integration. So we'll set two equations at a time equal to each other. Let's begin with the square root of x is equal to 1. All right, so we square each side and we get x equals 1. So this point here is 1 comma, and when x is 1, y is 1. So that was easy. This point here, the second point, we have to set y equals 1 to the line negative, the opposite of x plus 6. So if we solve this quickly and we get x is 5, so this point is 5 comma 1. Because it's on the line y equals 1. And then this point is the hardest to solve for because we have to set the square root of x equal to the linear function. And to solve for this, we have to square each side. And we have to multiply this out. Get the quadratic into standard form. And let's see, can we factor this? I believe we can. And this factors into x minus 9 times x minus 4. So we've got two possible x's here. X minus 9 equals 0. Or x minus 4 equals 0. So x is 9 or x is 4. So here, when x is 9 and we put it into the square root of x function, y is 3. So, but when x is 4 and we put it into the square root function, we get y is 2. Now that's interesting. It looks like we have two intersection points here, but the intersection point that we have is this, 4, 2. Notice that this x-coordinate is 5, so this has to be smaller. Where is 9, 3? Well, 9, 3 would have been an intersection point if I had this full curve, y squared equals x. It would have intersected this blue line at 9, 3, which looks just about right. But we're not going to consider that. These are the corners of our region. Okay, so I'm going to erase this. All right. Now, we've just learned how to find the area between two curves in terms of x. So we imagine a vertical rectangle in our region. Okay, now this one I have to pick a color. I'll pick gray. I don't know if this will work. Gray. Okay, and let's try this. Okay, and so if I draw a vertical rectangle here, the height of this rectangle would be the red curve minus the green curve, right? And that seems to be consistent all the way here. It's always red minus green. And as I go through the region, notice everything seems okay until I hit here. Okay, to the right of x equals 4, the vertical rectangle does not hit the red curve anymore. It hits the blue curve. Top minus bottom would be blue minus green. That would represent the height of the rectangle in that region. So if we were to do this using vertical rectangles, okay, so with vertical rectangles, we would need two integrals. One for this region between x equals 1 and x equals 4, and another one in this triangle, which we really don't need a rectangle to get the area of a triangle, but let's try. So for region 1, the integral would be from x equals 1 to x equals 4 of the top curve, which is root x, minus the bottom curve, which is 1. And remember, if we're going to represent this in terms of x, y has to be isolated. So y equals 1 and y equals root x. And then we'll get the area of region 2, and that's from x equals 4 to x equals 5 of the top curve, which is the line y equals the opposite of x plus 6, so I just write the opposite of x plus 6, minus the bottom, y equals 1, so I write 1. And we evaluate this accordingly. So let's try it. Okay, first we'll combine like terms. Then we'll integrate this. And again, this is all the power rule. So I'll pause the video here, and I'd like you to try it yourselves. So when we anti-differentiate x to the 1/2, we add 1 to the exponents. We get x to the 3/2 over 3/2, or times 2/3, minus the integral of 1 is just x, from 1 to 4. And then when we anti-differentiate the opposite of x, we get the opposite of x squared over 2 plus 5x from 4 to 5. Now let's continue on the next page. So using the first fundamental theorem of calculus, we substituted 4 into the antiderivative, and then 1 into the antiderivative, put parentheses and subtract, and then in the other piece we substituted 5 into the antiderivative, 4 into the antiderivative, and subtracted. Now let's work this out. So in the first piece, 4 to the 3/2 means the square root of 4, which is 2 cubed. That gives us 8. And then we distributed the negative here. And then finally, here we have negative 25/2 plus 25. Okay, 4 squared is 16 times negative half is negative 8. But I distributed the negative. I got positive 8 minus 20. All right, now what I like to do is I'd like to add the fractions with thirds. So this is how I used to do it when I was your age and I took AB calculus. So 16/3 minus 2/3, right? I would add those. I get my 14/3. And then I have minus 25/2. I don't have another half to subtract, so I'll carry this down. Okay, and then I add the numbers. Negative 4 plus 1 is negative 3, plus 25 is 22, plus 8 is 30, minus 20 is 10. I think that's right. Let me just double check it. Negative 4 plus 1 is negative 3. 22, 30. Okay, I think that's right. It's plus 10. And then, of course, we put everything in terms of sixths. And when we work this out, let's see what we get. So the answer for this comes out to be 2 1/6. And again, we could get a common denominator of 6 here. So I multiply the 14 by 2. I multiply the 25 by 3. And I multiply the 10 by 6. And that should be 2 1/6 when we simplify it. So we saw that if we use vertical rectangles, it's quite tedious because we have two regions. But there must be another way to do the problem. Let's take a look at the region one more time. Rather than using a vertical rectangle to span the region in question, we could try using a horizontal rectangle. And by horizontal, we have a rectangle that looks like this. Now, here it's like rotating, treating the y-axis as the x-axis, so that we could sum up the areas of these horizontal rectangles. Except how would we get the area of such a horizontal rectangle? That's the question. All right, let's think about this for a minute. And notice here, the top of the rectangle now is on the right. Here's the top of the rectangle relative to the y-axis. And the bottom of the rectangle is on the left. So it would appear that the length of that horizontal rectangle would be right minus top minus bottom, or in this case, right minus left. So here we have the following. To represent the area of any such rectangle that is horizontal, we would take the right function minus the left function. But there's a catch here. We cannot integrate with respect to x. The height of the rectangle is a horizontal distance. It's horizontal, so how can we represent this horizontal? Well, if we pick a point on the line y equals the opposite of x plus 6, any such point can be represented as x comma the opposite of x plus 6, which is the y value. But there's another way to represent the same point in terms of y. If we take the equation y equals the opposite of x plus 6 and solve for x, we could represent the same ordered pair as follows: 6 minus y, comma, y. Now, we never ever do this when we plot points, but any point on the plane can be represented in terms of x or in terms of y, depending on the situation. So when I take a look at this curve here, this horizontal distance with respect to y would be 6 minus y. It's the distance from the y-axis to a point on the blue line. And in the same way, any point on the red curve could be represented as, with coordinates in terms of x, x comma root x. But in terms of y, if we take this equation and solve for x, we get y squared. We can represent the same point as y squared comma y. So here we integrate with respect to y. And again, because it is this horizontal distance, okay, I should put it in red, this blue distance to the y-axis would be represented as 6 minus y. And this red distance from the y-axis to the red curve would be represented as y squared. So that the height of any such horizontal rectangle would be top minus bottom or right minus left. So our integral would be, it would be 6 minus y, which would be the right function, minus the left function, minus y squared. We integrate with respect to y, and the limits of integration have to be two horizontal lines. And the two horizontal lines that bound this region would be y equals 1 and to y equals 4. Well, I'm sorry, y equals 2. So that all the vertical lines become horizontal lines. So it's from y equals 1 to y equals 2. The tricky part is that we have to solve each function and isolate the x to express it in terms of y. Now let's see if we get the same answer as before. And notice we only need one integral because the right part, or the top, always hits the blue line, and the left, or the bottom, always hits the red curve. The antiderivative is 6y minus y squared over 2 minus y cubed over 3 from 1 to 2. And now we use the first fundamental theorem of calculus. We substitute the upper limit of integration and then the lower limit of integration. Don't forget the parentheses. And this is so much easier to compute than the other one. Let's try it. We get 12 minus 2 minus 8/3 minus 6 plus a half plus a third. I distributed the negative. And now let's combine and let's see what we get. So working it all out and combining the integers and the fractions, we do get 2 and 1/6. And we see that if we integrate with respect to y, which requires a horizontal rectangle, then we only use one integral. Okay, so let's summarize here. And wait, I just wanted to box my answer here. So this is our answer, which is consistent with the other one. So to summarize, some regions are best treated by regarding x as a function of y. So let's write that down. So if a region is bounded by the curves with the equations x equals a function of y and x equals some other function of y, g of y, y equals c and y equals d, where f and g are continuous, and f of y is greater than or equal to g of y for the interval y between c and d. Okay, so let's look at the figure. So here, all right. So if we think of this as a function of y, let's call this our x equals f of y. Okay. Actually, let me just make it a little bit better here. Okay, so let's make this like that. Okay. And let the other function, g of y, look something like this. and y equals c and y equals d, we could make this d and this c. Then it's beneficial for us to use a horizontal rectangle. Well, let me put that in green. Now, it's really the same, except we're treating the y-axis as the x-axis. Think of it that way. So if you rotate this 90 degrees counterclockwise, and the y-axis is towards you, you see that it's the same analogy. So delta y would be this width, and the height would be the right minus the left. So we could write this. The area bounded between these two curves is the definite integral from y equals c to y equals d of the function on the right, but we have to solve for x, minus the function on the left. And again, we solve for x. And we integrate with respect to y. And that is the idea. And we don't use this as often as vertical rectangles, but once in a while, it's more convenient to do the problem this way because we only deal with one integral. So remember, it's right minus left. But we have to solve for x. So there's additional algebra involved there. Okay, let's take a look at another problem. Okay, let's find the area bounded by the two curves x equals y squared and y equals x minus 2. All right, so we have to set up the problem. We must sketch. So let's sketch these two. So x equals y squared is like a parabola, but it's rotated, and y equals x minus 2 has a negative y-intercept of negative 2 and a slope of 1. So my sketch looks like this, and the region is between these two graphs is here. Okay, now the next step is to find the points of intersection. Without the points of intersection, we will not know our limits of integration. So we'll set these two equal to each other. So to find points of intersection, so if we have y equals x minus 2 and y equals x squared, there are lots of ways to solve, but we could just set, oh, I'm sorry. Yeah, I think I wrote that backwards. X equals y squared. X equals y squared. What we could do is we could substitute the y squared directly into the line. So we have y equals y squared minus 2. And if we solve that quadratic, we can factor y minus 2 times y plus 1. So, and we get y minus 2 equals 0, or y plus 1 equals 0. And we get two possible solutions for y. Y equals 2 or y equals negative 1. But what would be those x values? Well, we could substitute these back into the one of the equations. So when we substitute y equals 2 into x equals y squared, we get that x is 4. So 2, 4 seems to be one of the intersection points, which looks about right. And then when y equals negative 1, if we substitute it back in here, x equals y squared, we get x equals 1. So this intersection point is 1 comma negative 1, which is about right. Okay, now we have to decide, to get the area bounded by this region, which rectangle would be most beneficial? Well, I always start with a vertical rectangle and see if the top and bottom span the same two curves. So let's try it. So if we draw a vertical rectangle here, It looks like the top hits the red curve and the bottom hits the blue curve. But there's a problem right here. Because of this sidewards parabola, the vertical rectangle would hit the parabola, top and bottom both twice in the red region. So if we were to use a vertical rectangle, we would need two integrals. All right, let's take a look at that since we're on vertical rectangles. So looking at this, if we use a vertical rectangle, we would have to integrate with respect to x. Oh, let me just change the color here. Okay, so we integrate with respect to x. Automatically with respect to x. Okay, so we have two regions. We've got this region, number 1, and this region, number 2. Okay, because the top changes. I should say the bottom changes in region 1. Let's do region 2 first, and with respect to x. So region 2 would be the definite integral from x equals 1 to x equals 2 of top, which is the parabola. But let's keep that in mind, that this was x equals y squared. So if we solve for y, we get positive or negative the square root of x. So this is the combination of two curves. Y equals positive root x is above the x-axis, and y equals negative root x is below the x-axis. So in region 2, it would be the top, which is positive root x, minus the bottom, which is still the line x minus 2 with respect to x. And for region 1, well, that would be from x equals 0, which is right at the vertex of this so-called sidewards parabola, to x equals 1 of the top, which is root x, that's the top piece of the sidewards parabola, minus the bottom, which is still the red piece, but the bottom part of this sidewards parabola, which is minus negative root x with respect to x. And we would integrate that and solve to get the answer. Notice that that is quite involved. This is region 1. However, let's try a horizontal rectangle. So here I've sketched the region again with the intersection points. But if we use a horizontal rectangle, with a horizontal rectangle, we would have to integrate with respect to y. But notice that the right function, or the top of the rectangle, always hits the blue line, and the bottom of the rectangle, or the left side, always hits the red curve. So with horizontal rectangles, we would need one integral. So again, the catch is we have to isolate x. So let's look at our curves again. So for x equals y squared, x is already solved, so we just express that in terms of y. In the other one, y equals x minus 2. When we solve for x, we get y plus 2. So note that we will be using these expressions, the y plus 2 and the y squared, in our integrand. And what would our integral be? Well, again, the area would be y limits of integration. The two horizontal lines are y equals negative 1 to y equals 2. And that's why we need those intersection points. Negative 1 to 2 of the right function. The right function is the line, but in terms of y, that's y plus 2, minus the left function, which is the sidewards parabola, which will write y squared. dy. And notice that this is so much easier to integrate than our other problem. So what I'd like you to do now is to pause the video and evaluate this using the first fundamental theorem of calculus by yourselves, and then restart. So the antiderivative using the power rule is y squared over 2 plus 2y minus y cubed over 3. We substitute the 2 into the antiderivative, the negative 1 into the antiderivative. Please put parentheses, and please put parentheses around your negative numbers when the one of the upper or lower limits of integration is negative. And then very, very carefully evaluate if you don't have a calculator. The chances of making an error are very high here because there's so many little things that could go wrong. But the final answer comes out to be, I believe, 4.5. A good exercise is to evaluate the integral that we wrote on the previous page in terms of x and verify that the answer is 4.5. All right, so that takes care of our lesson dealing with area between two curves, and we would integrate in terms of y. So remember, when we use horizontal rectangles, and again, we don't use them that often, but when we use them, the horizontal rectangle spans the region where the right curve and the left curve are consistent throughout the region. And when we use a horizontal rectangle, we take each function, solve for x, so that we could express the function in terms of y, and we integrate with respect to y. All right, so that takes care of our lesson dealing with area between curves using horizontal rectangles. Have a great day.